Wine and other grape-based spirits are considered social beverage staples in many cultures across the world. As a result of globalization, international demand for imported wines has grown substantially, and Ontario wines are no exception. One of the biggest setbacks to wine production in the province is the management of solid grape waste, which is better known as grape pomace. Grape pomace is made up of the seeds, skins, and stems of grapes, and it accounts for about 20 to 25% of the total weight of the grape. The pomace does not make very good fertilizer due to its acidity, and it can attract a lot of bugs and rodents, so it is not suitable for spreading out on vineyard grounds after the harvesting season is over. Many of the world's leading wine exporters, including France, Italy, and Spain, have identified alternatives for the pomace after the winemaking process is complete. Ontario, however, does not have the same winemaking capacity as those countries, so alternatives for disposal are a lot more limited. Therefore, Ontario farmers often have no choice but to pay expensive disposal fees to have their pomace sent to a landfill. So this semester, we set out to provide alternatives that would divert the pomace from the landfill. Our ideal solution would use as much of the pomace as possible, be technologically feasible, and maximize revenue for farmers without inhibiting normal winery practices. The solution also needed to be more environmentally responsible than conventional landfilling. The alternative that we identified as being the most promising for implementation is an on-site anaerobic digester that uses gas from decomposed grape pomace to generate electricity on winery grounds. We limited the scope of our design to Ontario wineries, specifically those in the Niagara region, and compared the feasibility of the project for different sized wineries.
The design process that we defined has 7 steps that encompass the entire process of this design project. The first 2 steps were to identify and fully define the scope of our problem. This was done by doing research on the vinification process, the waste produced, and the current solutions. From this research, we were able to fully define our problem, the scope, and the constraints and criteria of our project. Once these steps were concluded, research and brainstorming were started as part of steps 3 and 4 of our process. Brainstorming and individual research led to the creation of 4 main design solutions that include ethanol production, bioplastics production, phenol extraction, and anaerobic digestion. These designs were compared and evaluated to decide on the best course of action, which is to design an anaerobic digester to valorize the solid waste into biogas. At this point of the process, we have finished optimizing the design by performing necessary calculations to prove its feasibility and effectiveness. The next step will be to finalize the design and communicate this design in the final report. The anaerobic digestion of winery waste involves using bacteria to break down the waste into biogas and digestate. This system was modeled for a small, average, and large-sized winery to fully understand the benefits and efficiency of implementing this system at each site. The process will require a pretreatment to maximize the production of biogas, especially for a smaller winery with a smaller feedstock of waste. The pretreatment chosen for this process is to mix the waste with water to produce a liquid with the correct concentration of solids and a higher amount of soluble organic matter. Once the material has been pretreated, it will be transported into the digester. This process will use a mesophilic or low-temperature digester for a simpler and more cost-effective design. The digester will be operating and continuously fed biomass for 120 days and will have a retention time of 20 days. As the waste breaks down, the biogas produced will naturally rise to the top of the tank where it will be removed for use. The biogas that was produced will be separated into methane and the other byproducts, mainly carbon dioxide with traces of water and hydrogen sulfide. The methane will then be fed to a combined heat and power unit that will generate electricity and recover heat lost in the process. The electrical output generated is 1.6, 3.8, and 10.7 kilowatts for the small, average, and large winery respectively. After calculating the recovered heat and the heat used to maintain the temperature of the reactor, the net heat production is 1.4, 4.2, and 14.5 kilowatts for each winery size respectively.
To keep capital costs low, a plug-flow style digester was chosen as an on-site solution for Ontario wineries. A plug-flow digester operates under gravity flow conditions, with no need for pumps or any form of mechanical agitation. The solution of solid grape waste, called a substrate, will enter the digester from an elevated receiving vessel and flow into the digester tank. The liquid substrate entering the digester will displace the same volume on the exiting chamber. To ensure anaerobic conditions, valves on the entrance and exit will be closed except during the loading time each day. A plug flow digester requires the maximum solids content of the digester to be 15%. Therefore, a small percentage of the wastewater produced by the winery is to be combined with the substrate to produce the 15% solids. The final volume of the digester tank is based on the 120-day digester operating time and a hydraulic retention time of 20 days of a given volume. 20 days is the recommended time for this type of digester in order to maximize methane production. The final dimensions from each digester tank were optimized to minimize surface area while maintaining correct proportions for a plug flow digester. The digester tank will be made from reinforced concrete to maintain low costs and provide corrosion resistance. The thickness of the digester tank wall was determined based on the pressure force of water on the tank walls when the digester is full. Simulations were conducted for all three digester sizes. To account for any error associated with the water pressure assumption, a factor of safety of 2 has been applied to simulations. Concrete fails first under tensile loading conditions, and simulations were able to determine a wall thickness, which ensured a minimum safety factor of 2 is maintained throughout the tank design. Covering the digester tank will be an insulated high-density polyethylene cover. This portion of the digester provides space for the methane gas to accumulate. Methane gas from this region of the digester will be piped into the combined heat and power unit for electricity production. The digester tank must be kept at a temperature of about 40 degrees Celsius to function properly, so a portion of the heat created by the heat and power unit will be retained to maintain this temperature. 4 inches of insulation are present along the exterior of the tank to minimize heat loss. For an average winery, about 45% of the heat produced from the heat and power unit will be used to maintain the digester temperature. The remainder of this heat will be available to other areas of the winery.
Early estimates indicate that the payback period ranges between 14.5 years and just over 20 years. The average size winery had the lowest payback period, while the small winery had the highest. The large winery had a payback period similar to the average winery at just under 16 years. For all three scenarios, the majority of cost savings come from the electricity generated, with the remainder coming from the recovered heat. The combined heat and power unit and the concrete made up the largest portions of the project's capital cost. While workplace injuries around anaerobic digesters are very uncommon, significant hazards still exist that must be accounted for in the design of the digester. Biogas accumulation poses a significant asphyxiation hazard, especially if the gas accumulates in a confined area. Biogas consists of mainly methane and carbon dioxide, both of which are colorless and odorless gases, making it nearly impossible to identify their presence. Trace amounts of hydrogen sulfide also exist, which is a highly poisonous gas even in low concentrations. Biogas is also highly flammable and explosive, meaning that no sources of ignition can be present near the digester. Electrical hazards exist around the transformer and the combined heat and power unit. Electrocution can occur from high voltage wires in the transformer or from arcing between the electrical panels and nearby conductive surfaces. Electrical fires can also occur and must be taken into consideration. The digester tank will be located at least 50 feet away from the winery or any area where people may be working for an extended period of time. The risk of asphyxiation is greatly reduced since the digester is located outside. Wall-mounted gas sensors will also be installed inside the generator room to alert anyone nearby if a dangerous level of either biogas or exhaust gases are accumulating. Warning signs must be installed in highly visible areas around the digester to warn those nearby of asphyxiation, explosive, and electrocution hazards. These warnings must make it clear that no ignition sources can be present within 50 feet of the digester. Transformer boxes and electrical panels must have covers and be locked out. Class ABC fire extinguishers must be present nearby so that electrical fires can be extinguished.
The two main aspects of our design that have environmental and social implications are that it creates electricity and that it uses grape pomace that may otherwise go to the landfill. Producing electricity is environmentally beneficial because it reduces demand on the electricity grid, which lessens the need for the use of resources like nuclear fuel and natural gas. Using pomace biogas as an electricity source is also renewable because new grape pomace is created each year, and it emits no greenhouse gases into the atmosphere. Diverting pomace from the landfill also has environmental benefits. When pomace is in the landfill, it lacks the necessary oxygen to decompose properly, so it rots and produces methane, which is a powerful greenhouse gas. By using pomace in our anaerobic digester instead, that methane is captured and turned into electricity instead of being emitted into the atmosphere. The leftover digestate is then suitable for use as fertilizer in the vineyard, which helps promote a circular economy framework in the winemaking process. There are also social impacts to be considered with our design. Producing electricity from anaerobic digestion will reduce the peak energy demand from the grid. This makes the power grid more efficient and less expensive by preventing inefficient backup power plants from being used during peak times. It also decreases the chance of power failures by reducing strain on the grid. There are also social benefits associated with diverting pomace from the landfill. Landfilled pomace can leach any pesticides or fertilizers used on the grapes into the environment, which can become a public health threat by contaminating the water supply. Another public health risk from pomace in landfills is that it attracts pests, which can spread diseases. Wineries that currently landfill their waste can avoid the public health consequences associated with it by using the anaerobic digester that we designed. So this means that our design is not only a source of revenue for wineries themselves, but it also has a variety of broader environmental and social benefits stemming from the fact that it creates electricity and diverts grape pomace from the landfill.
Our design concept is currently most feasible for wineries of average size. We would like to accommodate larger and smaller wineries as well so that as much waste as possible can be diverted from the landfill. The cost of implementing this process on winery grounds is currently also very high, so that in the future we anticipate finding ways to reduce the digester costs. This way, investment is not prohibitive to any wineries. This concludes our presentation. If you have any questions or comments about our design concept, please contact us. Thank you for listening.